Yeah, hi, hello, good morning, all of you. Fresh morning with what a topic, a big topic, big weightage, electromagnetics, really a big topic and a very rich scoring topic in second PU, both in CT and NEET. And here, this topic, huge number of titles, huge number of concepts. Like I first list out for our crash course, what we'll do is electromagnetics will divide first into the magnetic effects of currents. The second one would be the mechanical effects caused by the current carrying conductors. Now, in the first part, the magnetic effects of electric current, we begin with these Biot-Savart's law and Ampere's circuital law. Of course, I don't want to discuss those conceptual things. For that, please go through your class notebook. Remember, this is our crash program for CT NEET, not an integrated class, and that is why I ask you to go through your class notebook for these concepts of both Biot-Savart's law and Ampere's circuital law. Now, the second part would be the magnetic induction produced by current carrying conductors is the topic. Big topic, big formulae, big questions. We know that as that experiment established that every current carrying conductor produces magnetic field around it, right? So based on that, we'll now deduce, or in fact I will go on listing all the expressions for magnetic induction produced by current carrying conductors with different shapes, both magnitudes, and also the most essential part of this topic would be the sense of direction. Because magnetic field, magnetic induction is a vector and whose direction has to be well defined. And in each of the examples, along with the magnitude, we also give rules. Remember, we give rules for finding the direction of magnetic induction. And then the mechanical effects of electric current. We begin with the charge in an electric field. Then current carrying straight conductor in external magnetic field, charge in magnetic field, current carrying conductor placed in external magnetic field, then current loop, so on. Like that. So this topic, in this present session, what we would do is, we do the magnetic induction produced by current carrying conductors in different cases, both expressions and as well with few examples as well along with. Now here you see, this topic we use two vectors of magnetism. One vector is magnetic induction strength, capital B I have taken, you see. B bar, the magnetic induction strength, it's a vector quantity. We define it as flux density. Flux is the magnetic flux. Similar to the electric flux, we define magnetic field and magnetic flux. So this is what is magnetic flux, and it's a scalar quantity, and its SI unit is Weber, and this one is area of the cross section through which we are talking about the flux. Therefore, flux density is what is magnetic induction. SI unit Weber per meter square. Also we can write it as Newton per ampere meter, or it's otherwise called as Tesla, the SI unit. And also remember, we write the CGS unit also. The CGS unit of capital B, the CGS unit is, yes, GAUSS, Gauss. I write it as capital G. And also remember the conversion. The conversion is 1 Gauss is 10 power minus 4 Tesla. Whenever you are given B in terms of Gauss, the multiplication factor is 10 power minus 4 will convert into Tesla. Every time I have told you, any data, all the parameters try to always always write in SI units for your answers. 1 Gauss is 10 power minus 4 Tesla, and of course, as I have told, B bar, it's a vector direction we will show when we are talking about a particular case. Also, another important vector is moment of magnets. Magnet is a dipole, and dipole moment similar to the one we have defined for electric dipole. And for this magnetic dipole, here I am mentioning the SI unit because I may be using that in our examples. Therefore, I am writing it as ampere meter square. It is not ampere per meter square. Please do remember, it is ampere meter square. Even you can write dimensions on your own, and which is a very important point, so that 1 mark is easy scoring forever. See here, if you are writing the dimension formula for capital B, what is this? Newton. Newton is m/L/T minus 2. Denominator again, one more meter, you find that L term is cancelled. Therefore, this is m/T minus 2 in the numerator, and I, the current. We write it as I or A both, any of them, right? Therefore, it is m/T minus 2, I minus 1 will be the dimension formula. Similarly, what will be the for moment of the magnet? So magnetic moment you will write as L square, meter square is there, therefore it is L square and A for I. Now you see here it is independent of length. Capital B dimensions independent of length. Here it is independent of mass and as well as time, because you will find the examples which of the following quantities is independent of masses or independent of times, like that. So every time you please write the dimension formula by knowing the unit, it will give you a very good idea about the whole concept. So these are the two vectors to begin with. And as I have told you, please do remember, for crash course we cannot get into the complete detailed discussions of all the things. Therefore, those Biot-Savart's law and Ampere circuit law, you please go through your notebooks. Now here, begin with. Let us take up this case along with examples also. This is the case of capital B due to straight conductor, of course carrying current. Here I have shown a conductor. Here I will call it as the conductor of finite length. Conductor of finite length. And don't see, when I am writing an expression, don't think that I am adding more and more number of formulae. In fact, it is only one expression. When you have a substitution of special cases, you will get 2 or 3 other formulae. That is what I am showing you here. Don't feel it as a list of formulae, right? So this is straight conductor, and I have taken the ends as A and B. So since ends are shown, it is of finite length. It carries current I. Here I have shown upward current. It can be either upward current or downward current, or while placed horizontally, current to the left or right. And it is an important point when it comes to the direction of magnetic induction, which we will discuss in the due course. So this is a current carrying conductor, finite length. Now here I have shown 2 points. 2 points. One point is P1, which is the lateral point. P2 is a point along the conductor, you will find it. So this is a point along the conductor. Now what is the rule? For this lateral point, at a distance r from the straight conductor, first we have to join the point P from the ends. And you mention these angles as alpha and beta. So the point of observation, yes, connected, joined with ends, and then you are writing these angles. Now I am writing B at P1, which is the lateral point, is mu naught I by 4 pi r times sine alpha plus sine beta is the expression. Now here, what about mu naught? Mu naught value is 4 pi into 10 raised minus 7. And I will write the unit as Newton per ampere square, otherwise called Henry per meter. Remember this mu naught value 4 pi into 10 power minus 7. So in all the cases, mu naught by 4 pi, I will take it as 10 raised minus 7. Look at this unit, Newton per ampere square. Therefore, writing dimensions is also very easy. Newton m/L/T minus 2, and this is ampere square, which will be I minus 2. So writing dimensions will be easy if you remember this one. So generally we write it as Henry per meter. So this is one thing. Now remember, here we are writing also for P2. And this B at P2 is 0. Therefore, for any straight conductor, it produces magnetic induction at any lateral point, but not a point which is along the conductor. It can also be asked as an assertion reasoning question in some competitive examination, and the reason for that is according to Biot-Savart's law, the B proportional to sine theta is a rule. B proportional to sine theta is a rule, where theta is the angle joining the current element and the radius vector which joins the element and the point of observation. Now for a point which is along the conductor, theta will be 0 and hence sin 0, 0. For that reason, B at P2 is 0. Now this is the only expression that we have to remember, but now you see, generally this is a very least probable question. Most of the times we are given long straight conductor. Long straight conductor. Long straight conductor, for which what happens? Long means I don't know the ends. Therefore this is some point P, again a distance R, again carrying current I in any given direction. This is P. Now for this case what happens? If you now wish to join the point P with the ends, both alpha and beta, this will become like, these are the lines that you get. Therefore here in this case, long straight conductor alpha is equal to beta is equal to 90 degrees. So sin 90 plus sin 90, it will be 2. Therefore, remember, long straight conductor, which is the most probable case in all our examinations, B at P is given by mu naught I by 2 pi R. Very important expression. Very important expression. And please have a good observation. Here P is taken, which is a lateral point of course, but this point P is not opposite to any one of the ends. Why? Because in the same case, for example, one more example I will show you. Supposing this is a long conductor again carrying current I. This one is a long end and one of the ends only I know, the other end of course I don't know. Once again the case of a long wire. Now supposing point P is here, located at a point, this point is exactly opposite to one of the ends of the conductor. Then what happens? In this case, one angle alpha is equal to 0, the other angle becomes 90 degrees. Therefore, in this case, B at P is equal to mu naught I by, yes, 4 pi R, because it is sin 0 plus sin 90. So it is only mu naught I by 4 pi R. Please watch these things carefully. Any question when you are given, first thing is that whether it is finite length or infinite length. Second one, if it is again infinite length, two possibilities like a point P, lateral point which is somewhere in between the ends, then mu naught I by 2 pi R. Otherwise, infinite wide, but the point is opposite to one of the ends, mu naught I by 4 pi R. Denominator is a change we have to remember. And in both the cases what you will find that for long wire, we write B proportional to 1 by R, B1 by B2 is equal to R2 by R1. Therefore, now this field produced by a straight conductor carrying current is always a non-uniform magnetic field. Two reasons, because B changes both in magnitude and direction. Now comes, when I said direction of capital B, here I have given only the magnitude, right? Now let us come to the all important point of direction. And remember, when I am giving you the direction sense, it is not that you should watch somebody doing that action. It should be your act. So use your right hand, use your left hand whenever I say as a principle. Now, to find the direction of capital at this point, which is the lateral point. What is the rule? This is what is Ampere's thumb rule, Ampere's right hand rule. Now this is called grip, right hand grip. And supposing this is a straight conductor and I held in the right hand, I held it in the right gap, such that now here you will find this is the thumb and this is what is the curl of the fingers, remaining fingers. This is the curl of the fingers and this is straight. Now for straight conductor we are telling the rule that in a straight conductor, if this thumb represents the direction of current, the curl of the fingers represent direction of field lines. Again I am telling you this is representing field lines. Now in this case, how to write the direction? See, Supposing this is a straight conductor and this is some point P, it carries an upward current I. P is a point to your right and Q is a point to your left. Then how to find the direction is, yes, please use your right hand. Use your right hand, and most important point is that I am writing it on a vertical plane. In the examination you will see paper as a horizontal plane. That is why you have to use your hand. See, thumb representing the direction of current. Yes, my thumb is upwards. Now look at these fingers. These fingers are entering into, right? This is how you are writing. This is how you are writing. Therefore at the point P, these are entering inwards. Into, therefore I am writing it as a cross. So this is inward. This representation shows B is inwards. When it is inwards, and we know that magnetic field lines are always closed curves, if it enters on your right hand side, it should leave the surface from your left hand side. Therefore here it is, yes, directed outward. So these are the two symbols we are writing. Right? This cross represents normal to the plane and inwards. This one, a circle and a dot, or otherwise simply dot represents normal to the plane and outwards. Dot outwards, cross is inwards. See, without using this right hand rule, it's very difficult to find answers in our NEET or CET, because we always calculate the net magnetic inductions. Where it is not the algebraic summation, we have to consider the vector addition, and hence direction is the key. Use your right hand rule, and this is the rule only for straight conductor. Because in the case of circular conductors or arcs, we will have a change in the rule. We will speak it later. This one, the thumb direction of current and the curl of the fingers representing the field lines. Once we get the field lines, what we did is drawing the tangent at a point, which is the property of magnetic flux. And I have shown you here, when we are drawing the tangent, this is inwards and this is outwards, right? Now supposing I show one more example, horizontal, and it carries current towards your left hand. Now do it for yourself, use your right hand. Now I consider a point P and here another point Q. Now how to use this? See, thumb, current direction, yes. Now what you find, your fingers are leaving the board. Therefore this is coming outwards. I will show a dot, and since it is outwards, other side it will enter. Therefore here a right cross. So this is how we make use of expression, this capital B expression, along with the sense of direction. Now let us find some examples for that concept that we have explained. Now here says long straight conductor held vertically, and this is a horizontal plane. It carries a current of 3 ampere. The conductor, long conductor it is said. Now the question is that find location of null point in Earth's magnetic field is the question. Now we know that Earth's magnetic field, the horizontal component is always directed from geographical south to north. So this is an important point to remember. Whenever we are using B, in which we are taking the component BH, the horizontal component, here it is given set to be in horizontal plane. So on the horizontal plane you are finding the null point, the magnetic null point. Therefore BH, remember direction is geographical south to north is the one. Now what is the concept of null point? First let us write. What is that null point? That capital B, and of course you will be given data. And I said data, BH value is 36 micro Tesla at a given point, supposing it is a given data. Now what is the principle, or what is the condition for null point? Capital B, due to straight conductor, current carrying straight conductor, should be equal and opposite to the Earth's magnetic horizontal component. Then two vectors equal and opposite. The resultant will be 0. That net induction 0 is what is called as null point, the magnetic null point. Now let us write the condition. B due to straight conductor, therefore I am writing mu naught I by 2 pi R, where R is the distance of the null point from the straight conductor, which we have now to determine, and this value is equal to BH given to be 36 into 10 rise minus 6 don't forget this submultiple. Micro Tesla, I said 36 into 10 rise minus 6. What is this? Mu naught by 2 pi. Mu naught I told you 4 pi into 10 rise minus 7. Therefore this is 2 pi. Therefore this is 2 into 10 rise minus 7. And this I is going to be 3 ampere by 36 into 10 rise minus 6. And this is what is the value of R. So what you will find that 36. So the answer is 1 by 6 into 10 rise minus 1. 1 by 6 into 10 rise minus 1. This is all in meters. We have substituted. Therefore, shall I write it as 1 by 60 if I write. 1 by 60 if I write it, it becomes 10 rise minus 2. No. 1 by 6 into 10 power minus 1, I will write it as 10 by 6 into 10 rise minus 2 meter, which will become centimeter, right? So the answer is 10 by 6 centimeter. We got the distance. But the point is about the options. Simply the distance given, then the number is 10 by 6. But now you see, if the options are given as the 10 by 6 towards north of the conductor or due south of the conductor, east of the conductor, how to find that location. Here I am showing you this same figure. This is the horizontal plane and this pen, you consider this as a straight conductor carrying current and that red tip showing the direction of current. Remember, we have told the direction of current is very key in all our examples where we are finding net magnetic inductions. Therefore, now here first, this is north I have taken, therefore this one is south. And therefore this one is east and this is west. So whenever you are writing about the directions, please do remember whatever you are facing, you take it as north, your back shows south, your right hand shows east and your left hand shows west. You follow this convention. Now here first let us write BH value. BH value is always, I have told you, from south to north, which I have shown with a blue vector. You can see here. So at every point, north, east, south, west, I have shown blue line from south to north, which is BH. And one more vector I have shown in the black color, which is nothing but this black color represents magnetic induction produced by a straight wire. Now use this right hand rule. Use this right hand rule, current in the upward direction. Look at this order. Therefore east. It is at east point it is acting towards north. At north point it is towards west and so on. Black line you will find an order, right? So because of that, what you will find? You will find that north and east, B and BH are perpendicular. I have taken all points equidistant. Look at this point. This is north point and south point where you will find B and BH are perpendicular. Root of B square plus BH square. No question of null point. And at east point, what you observe? You observe both B and BH are parallel. Therefore, effective is B plus BH. So it is a point with maximum magnetic induction. No question of null point. Now look at this point at west. At west, you will find that blue line and black line. Blue for BH and black for B due to the conductor. They are anti-parallel. Supposing if they are equal and anti-parallel, the net induction is 0. Therefore, now in this case, it is a null point due west of the conductor is the answer, right? When we are getting this west, when the current is upward, yes, the null point is west. Supposing in the same example, horizontal plane, vertical conductor carrying current and it is downwards, the null point will be due east of the conductor. So that is what is the importance of this right hand rule, and also in the examples we are writing BH and that is also an important thing. So now the answer is 10 by 6, 10 centimeter is the answer, right? Now let us see one more example. In this example also I have taken the case of straight conductors only, but not one, but here I have shown two conductors P and Q. Remember, said to be long straight conductors carrying currents 3 ampere and 2 amperes. And it is given to be parallel vectors, both upward currents are given. Now the question is that find location of null point. Find location of null point. Null point. In that case, we got only one null point. For a given conductor, straight conductor, single conductor, we got only one in the case of Earth's magnetic field. But here let us see. This question is find the location of null point, and this example he says neglect B due to Earth's magnetic field. Yes. You neglect Earth's magnetic field and find the null point is the question. Now let us here also see how is it a single null point or null points we get, what are the all different possibilities. Now let us consider some point over here. I call this as some P1 point to the left of P according to you. Then what happens? The current upward. Look at this. Look at my fingers. Use your right hand rule. What will find that at P1, induction due to P will be outwards and also due to Q it will be outwards. So at this point P1, the two vectors B1 due to P and B2 due to Q will be parallel. So when there is parallel, there is no question of null point. Similarly, you consider another point somewhere over here, I call this as P3. At this point what happens? Now you see here Q, look at my fingers, inverse. Due to P also the inverse. So P3 also, both B1 and B2 are parallel, but this time both are inverse. Here it was both are outwards. Therefore, here also no question of null point, because to get null point, you should have the condition of B1 and B2 anti-parallel. Now look at this point, I consider some point P over here, which is at a distance. Supposing I call this distance as D, I have taken from P, where the current is some I1, like that. Now supposing if this is what is D, the distance here, supposing it is D is the, R is the distance, parallel distance between the two straight conductors. Now at this point P here, P produces, right hand rule, inward, and Q produces outward field. Therefore there is a possibility for null point between the two conductors but not outside the combination. Right? So what is the condition we write? Mu naught I1, if I1 is the current carried by P, from which I have taken the distance. Mu naught I1 by 2 pi D is equal to mu naught I2 by 2 pi into R minus D, because this distance will be R minus D, equal opposite condition. Therefore you will get the expression as D is equal to R by I2 by I1 plus 1. I2 by I1 plus 1, have a small simplification, and this is all from I1, the conductor which carries a current I1 is the rule. Now according to the given example, R is given to be 9 cm. Supposing if I am finding the location from P, then I1 is nothing but 3 amperes. If you want to find the distance from Q, then 2 amperes becomes I1. Remember I1 and I2 when I am writing here, it is not that the order that is given in the example, but it is I1, the meaning is the current carried by the conductor from which we are finding the distance. So it is 9 by, yes, if suppose if I write 2 by 3 plus 1. So this is what is 27 by 5 centimeter. This is 5.4 centimeter. 5.4 centimeter is not the answer. 5.4 centimeter from P is the answer. Or else 9 minus, if you do, that will be the from Q. Now what do you find? The total distance is 9 and the distance is 5.4. Therefore the distance from 3 ampere is more and it will be lesser from Q. So null point is always closer to the conductor which carries smaller current is the rule. Larger current, more distance, smaller current, lesser distance will be the case here. Now this is the case I have discussed where both are carrying currents in the same direction, either both upward or both downwards, like that. Now after this example, I hope you have watched this solution. Now I will write it as a general case. How? I will write it as plus or minus 1 from I1, such that when do we use positive sign and when do we use negative sign? Positive sign for P and Q carrying parallel currents. Parallel currents. Then we have to use positive sign. In such case what happens? Null point will be between the conductors. Between two conductors we get, not outside. Whereas when do we use this negative sign? Negative sign for P and Q carrying anti-parallel currents in opposite direction. If one carries upward, the other carries downwards. If one carries towards right, the other carries towards left, like that. In such case, we have to use negative sign here. In such case, what happens? It will be outside the combination. Outside the combination, we will get a null point. That point, supposing if I reverse this current direction, what happens? You tell me. What happens? You tell me. It will be not in between, then it should be outside. Outside means either to the I'm telling you, with respect to you, to the left of P or to the right of Q. According to you, I am telling you, right? So now the point is that earlier we have told null point is always closer to the conductor which carries a smaller current. Therefore, if you get the answer, let me substitute and show you. This is 9 by I2 by I1, suppose 3 centimeter. I take 3 by 2, this time I write it as -1, which will be 18 centimeters, right? This is 1 by 2. So 18 centimeter from which one I am taking? 3 by 2 I have taken, therefore this one. From. So 18 centimeter, this side you will get, because it is closer to smaller current, therefore 3 amperes is a larger current and therefore more distance. Therefore, when you are finding the null point outside the combination, make sure which one is carrying a higher current or smaller current. Towards a smaller current, that you will get as a null point is an important thing. Now, one more thing to remember, in this case, supposing earlier we have shown 3 amperes and 2 amperes like this. Now, suppose if this is a null point, this is not a single null point that we get. Now, take this straight line. All the points on this straight line, yes, it will be null point. Therefore, locus of null points in this case will be straight line. We get infinite number. It is not one null point, but more number of null points, and the locus will be straight line. Similar example, but with a small difference. Again, 2 straight conductors. Example says X and Y are long straight conductors carrying currents Ix and Iy with the directions. Proper observation, please. Right? Ix and Iy, I am giving you the symbols. If number is given, you can substitute. Now the question is that find the locus of null points. To find that, here I have shown as a Cartesian coordinate system, x-axis, y-axis, first, second, third, fourth quadrant. Now you consider some point in first quadrant. Now let us see what will be the net magnetic induction at that point due to both of the conductors. Supposing if I take x if I take, look at this, current direction, then my fingers are inwards. And here you see, what is this one? Here also it is inwards. Why? Upward current, my fingers are inwards. Got the point? So at first quadrant, both B1 and B2 are inwards. Therefore, no question of null point. So whatever rule is there, the same rule will also be applicable here also. B1 and B2 will be parallel. First quadrant and third quadrant. Now you consider some point in the second quadrant. Again, what is the rule? What you observe is X direction of current. My fingers are entering inwards, but look at with respect to Y. Y upward current. Here my fingers are entering, therefore it leaves here. Therefore at this point, I now call this some point P, where we will find that second quadrant. Remember, direction of the current is all important in doing in any such example, case of 2 or more number of conductors carrying current. Second quadrant, at the point P, what do you observe? B1 opposite to B2. In the case both magnitudes are equal, then the net induction will be 0, that is what is the null point. Therefore, let me consider this is the point P which is at a distance. Remember, in our Cartesian system, distance from x-axis is always taken to be y, and distance from y-axis is taken to be x. So that is how I am taking. Now x is not the distance from x-axis, it is the distance from y-axis, and y is the distance of the point from x-axis, that is the conductor x you can call. Therefore now what is the condition you are getting? Mu naught Ix due to x I am writing, and at what distance it is there? Y is equal to, and 2 pi r, 2 pi y is equal to mu naught I y by 2 pi x. X is the distance from the conductor y. Therefore, what will be the result? You will find that y is equal to this. Y is equal to Ix by Iy times x. So this is what is the equation. And remember, this is y is equal to mx form. M is the slope. So what does it mean? In this example also we get large number of null points which will be lying. See, this is what we are writing. This is what we are writing. Now this is the straight line in the second quadrant and fourth quadrant we are getting, and therefore this slope, remember this slope is positive slope in second quadrant and fourth quadrant. And the most important is writing the equation along with the right sign conventions is very important. Options are very careful. Therefore now here y is equal to Ix by Iy into x is the equation of null point. See. So the concept of null point we have did in 1 or 2 or 3 cases, and one more example now I would like to show you. That this time let us consider a conductor of finite length. He don't mention that finite length, but the question we have to take that from the data. Here I show a question. See, ABCD is a square loop. ABCD is a square loop and carries a current I. Remember, this is a current loop. Nowhere current split is taking place. ABCD square loop, suppose this is of side L. A square loop of side L and it carries a current I. Now the question is, find the net magnetic induction at the geometric center O is the question. Now I will do it in a quick way because you have to use your right hands, remember. Now if I consider this as a square loop, each side now becomes finite because we know the end points, and therefore it becomes a case of finite length. Now look here, A, B, straight, carrying current upward, my fingers inwards, BC, look at my fingers downwards, CD, again here it is entering, outward, therefore here they will enter. So if you apply your right hand rule, what is that you observe? All the magnetic inductions due to 4 straight conductors at O are parallel. Number one. So all the vectors are to be added. Why? Because all are parallel, and accordingly here it is inverse. So we have to add 4 vectors, number 1 point. Like 4 vectors means we will get algebraic addition because they are parallel. One more thing is that everything is here is symmetric. All of them are same length and carries the same current. And also look at this point. Our rule was join the point of observation and the ends. Right? Now what is this angle? This angle will be 45 degrees and 45 degrees because it's a square, and these two are diagonals. Total angle 90, therefore equal angles 45 degrees and 45 degrees. And what will be this distance? You tell me now here. This is what is the distance. Total length is L, therefore here it becomes L by 2. Now let me write B due to AB is equal to B due to BC is equal to B due to CD is equal to B due to DA. This is one case. Remember, this is a current loop and this is equal to B I am writing. In such case, what is B? You write the formula mu naught I by 4 pi R. Now in this example that R is L by 2 into sin alpha plus sin beta. What do you observe? Sin 45 plus sin 45. 1 by root 2 plus 1 by root 2. Yes? 2 by root 2. Which is nothing but? Yes? It becomes root 2. So this is 2 root 2 mu naught I by 4 pi L due to single sign. Now we have told if I want at O, B at O is equal to all vectors are added, B due to AB plus DC plus CD plus DA. So what will be the answer? This is 4 times B, therefore this is 8 root 2 mu naught I by 4 pi L will be the answer. Like that. Now supposing I have told you, if I change geometry and you get it as a triangle, side L, and it is equilateral triangle, again current loop. The only difference is that instead of square, it is a triangular loop is the change. Then what are the simple changes you get? Instead of 4, you will get 3. So all inwards are all upwards, therefore it is to be added. So instead, now you see, there you get B at this geometric center O is equal to 3B is one result. And of course here I have taken alpha is equal to beta is equal to 45 each. The same if you write here, this angle is 120, therefore it means alpha is equal to beta is equal to 60 degrees. So what will be the answer that you get? Therefore B is equal to mu naught I by 4 pi. And what is this distance? The property of equilateral triangle, you remember? Centroid to the side, then you write it as L by 2 root 3 times. And angles are 60 and 60, alpha and beta values. Therefore I will utilize sine 60 plus sine 60, 2 times root 3 by 2. Therefore you will get it as root 3 times. Therefore it is 2 root 3, root 3. Its complete is 6 mu naught I by 4 pi L. Now you have to write it as 3 times. Right? 3 times you get. So final answer will be 18 mu naught I by 4 pi L for the case of a triangular loop. Like that, for a given finite length, we will have a geometry, and in that geometry it will be finite length. Now supposing in the same example I show a small change, then the 2 questions we can answer. What is that? See, supposing here same square loop is given. You call it A, B, C, D, but please look here. He has now given, yes, a current division. Now this is the current I enters at A, and this is the current that leaves at B. This is not a current loop. That is now a voltage source connected across AB. Then what happens? See, this I, now it will split. This is the branch ABCD and this is the branch AB. So current division, this is what is I1 and this is what is I2. Now the properties of resistors, you remember, these are 3 sides and this is only one side. 3 sides each R, then it will be 3R in, because all of them are undivided current 3R, and this one is resistance R. Therefore, now what you will write? I1 by I2 is equal to, in the inverse ratio of resistance, then it will carry only I by 3. I1 is equal to I by 3, I2 is equal to 2I by 3 is the first one. Earlier in this case it was a loop and all sides carry same current, but it is not here. The first. Second difference, you will find AB, BC and CD. Again the question is to find the net magnetic induction at the geometric center. Now here AB, BC, CD. All of them produce equal induction, right? Equal induction, what was that induction? 2 root 2 mu naught I by 4 pi L, and all of them are parallel. But B due to AB, here you see this one is inwards and therefore it is outwards. Therefore here what we observe is that B, AB, CD if we consider, B, AB, CD if we consider, supposing you got it as some B due to AB alone will be B, but with the negative sign I am writing because it is opposite direction. Look here please one more time. I am writing AB, BC, CD. All will add, okay, all will be added. No, this is not I by 3, 1, 2, 3, right? Yeah. So BAB minus B. Now here what happens? The 2 inductions, suppose I call it as B1 and this is B2, both have same magnitudes. Both have same magnitudes, therefore that ratio is 1. That ratio is 1, therefore net induction, yes, net induction is 0. Net induction is 0. I'm sorry, one more time, these are 4 resistors, right? So this is 1, 2, 3 and 3 parts and 1 part. Therefore I am sorry, this one is, yeah, this one is I by 4 and this one is 3I by 4. Yeah, take that. And that is why you get BAB equal to B. Here all the 3 will add and this carries 3 times current, and that is where both are equal. and opposite net induction is 0. Supposing asked the question of the ratio of magnetic inductions due to the two segments, the ratio is 1, they are equal in magnitude, but also opposite direction, hence net magnetic induction at this geometric center is 0. The same rule will apply for any other geometry, whether triangle or circle or any other geometry. Whenever you see such case of current split, the two segments carrying different currents and the magnetic inductions ratio of the two segments will be equal, that is 1, but the net magnetic induction is 0.